Okay, so the next one we're doing here is Arctic Circle daylight. So on the Arctic circle, there are 24 hours of daylight on the summer solstice, June 21st, which is the 173rd day of the year, and 24 hours of darkness on the winter solstice, December 21st, which is either day -10 or positive 355. And there are 12 hours of daylight and 12 hours of darkness midway between the summer and winter solstice on days 81 and 264. And we're supposed to figure out what are the max min hours of daylight in the Arctic Circle, use these values to calculate the amplitude and average value of the hours of the daylight cycle, then calculate the period and horizontal shift of the hours of the daylight cycle, use these values to calculate the parameters B and C for our model, and then use the constants from parts A and B to construct the overall sine model. So I think what we need to do first is think about what this graph is going to look like. So we know there's going to be a peak. And so we might have our scale over here. Okay. And we know somewhere over here is going to be, and then let's call this 24 hours of daylight, and then this is x equals 0. And so y equals 0 is, this is 0, 0. So y equals 0 the hours, and this is 24 hours, and this is a daylight. And so we know somewhere down here on the June 21st, the 173rd day of the year, we get 24 hours of light. And so then we know somewhere down over here, and wherever that is, that's going to be, so this is 173, this is going to be on 355, that's going to be 0 hours of light. And we know somewhere in between here, about, say right about there, and that's going to be day 264 and also 81. So we can go back this way and say, well, this is going to be on 81. And so we know those days. And so, and again, if we keep going over here, it'll be also on this edge over here. And somewhere over here, we'll have a 0. But what we really know is, well, we can't draw is what we really know. Let's try this again. So we know it's going to come down. Again, I can't draw. Let me try this again. On a computer, this is not easy, I guess. It's not easy on paper either, but that doesn't mean anything. Then we're going to hit another peak over here, and it's going to come down on this side over here somewhere. And we know that the max is 24, so that's going to be our max point. So if we take 24 minus 0 and then divide that by 2, that's going to give us 12 hours, and that's going to be our D, okay? And so 12 hours, that's going to be our average value. But guess what? If we take from here to here, and from here to here, A is going to be 12 hours as well. Because if we take 24 minus 12, we get 12. And if we take 12 minus 0, we get 12 here. Okay, so we know that. And so we know A and D, and so that's equal to D. So we know A's and D's. And now what we have to think about is, okay, well, what is that point versus what is that point? Well, that's going to be the 173rd day of the year. And that's going to be what, our June 21st. And so what's this day over here going to be? Oh, it's going to be June 21st as well. And so what is our period? Our period is a year, which is 365 days. Now, if we want to solve that, what do we know about that? Well, we're going to say 2 pi over b is equal to 365. And so b is equal to, if multiplied by b and divide by that, we're going to get 2 pi over 365. And then if we plug that into our calculator, and again, this is just something you can do on your calculator. You don't have to see me doing it, hopefully. We get approximately 0.0172 is going to be our B value, okay? Now, what else do we know? Okay, so now we've got B, we've got D, we need C, okay? And so that's the value here we need. Well, what is that? Well, remember, that's going to be part of our offset, because if we think about this, this is really kind of what it looks like, and we want that point there. So we need that offset. Well, that's 81 days when it actually is hitting that point there. And so it's a negative 81 as far as offset, because we moved right, and so it had to be negative. And so what we're going to do is we're going to say, okay, well, then what is C equal to? Well, our C is going to be equal to a negative 81 times our B, which was that 0.0172. And if we take that times each other, we get a negative 1.394 for our C. Okay, so now we've got our C, we've got our B, we've got our D, and we've got our A. So now let's use all those and write our function. So f of x is equal to A, which we said was 12. And so we have 12 and sine of B, and the B was the 0.0172 times x, and then we have minus 1.394, and then D was also 12. That was our average. And so that's going to be our equation, and that's hours. Okay, and so that's the amount of daylight, hours of daylight, and that's going to be for 0 less than or equal to x less than or equal to 365. So that's going to be our whole range of days. It's going to be that, and it's going to be on the x day, basically. Okay, so if we go back here, it's going to be on whatever x day we're on. So, okay. So that's how we do it. And I think the best way is to do this is actually draw this graph, because when you first look at it, you're like, what does all of these values mean? How does that work? And it can really confuse you. And so, drawing out, okay, on June 21st, we get 24 hours of daylight. Okay, well, June 21st, that's equal to 24. And then on December 21st, we get 0 or 24 hours of darkness, or 0 hours of daylight. So, that's here. And then after that, we can start thinking about what our graph looks like. Again, not perfect, but it gives us an idea. Then we can get our A, our average value, and then we can get our offset here, and then we can also get our period from here to here. So then we can get our B, and we get all our stuff. But again, thinking through it, plugging in the data as it is, and then working through is going to be the best way to do these. All right, so the next one here is going to be modeling. So we're going back to modeling, and it says the table gives the normal daily mean temperature based on a 30-year period, 1971 through 2000 for Phoenix, Arizona. Explain why the data should be cyclic. Well, that one's pretty easy, because every year you're going to have January through December, and then as next year is going to go January through December, and so it's a yearly period. Basically, it's going to be every 12 months is going to be the period. Now we're supposed to write a sine model for the mean temperature during the X month of the year. Then what is the period of the model? Does this period fit the context? And use the model predict the mean daily temperature in Phoenix in July. Is the prediction reasonable? Explain. All right, so let's go plug in this data into our calculator. Okay, so I've got the data typed in now, and so as you can see, January, February, we just put them into the actual numbers of the values, and then we plugged in our data over here. So our graph, kind of looks like this. It almost could be some kind of a quadratic, except it has this kind of tailing off here. And so what we're supposed to do is come up with a sine graph. So sine's down at the bottom, letter C. And so I'm just going to leave it on 3 iterations. That's good enough for here. And then we're going to go ahead and put that in vars 1, so then we can actually see what it is. And so this is our function. So we can write that out, and then we can put that into our thing later, 0.9550, 2.366, All right, so now what we need to do is we need to look and see what our graph looks like. All right, so I decided to go ahead and make it longer. Now, one key thing is if you try to do this, it's not going to work because you're normally in degree mode. Now we're doing sines and cosines. So what we have to do is we have to put this in radian mode. And so normally you're over here in degree mode, but like I said, this has to be in radian mode. So that's one thing we need to make sure your calculators are set up for. And so then it'll graph it properly. And so then, let's see, that's our sine model. So then what is the period? Well, now we need our equation. And what I'm going to do is I'm going to save that part for last. And I'm going to go to D, and we're going to predict the temperature in July. So I'm going to use a value. We want to find some value. And we want to find the temperature in July. Well, when is July? That's month 7. And we get 92.95 degrees Fahrenheit. So let's go back to our window over here and write what we have. Yes, it's yearly, it's a period. Now the sine model. Okay, so B, our sine model, maybe we want T of X, and that's going to be equal to, and we had 19.336 sine, and then we had 0.550x, and then we had a minus 2.366, and we had plus 73.687, and this is degrees Fahrenheit for the normal, basically for the mean daily temperature during the X month of the year. And so that all kind of goes right here. So we're kind of not going to write all that out. That's what it all is equal to. Now C, what is the period of the model? Now notice it says the model and not the context of the thing. So does this period fit the context? Because those are two different things. So our period, remember, is equal to 2 pi over b. Well, b is 0.550. And so if we do that, that's going to be 2, and that's going to, let me get to the 2 pi divided by 0.550. So that's going to give us approximately 11.4. And what does that equal to? Well, that's going to be equal to months. Okay, and so that's going to be our period. So every 11.4 months, it's going to be a period. Now, does that fit the context of the actual data? Well, the whole data is actually 12 months, and so we could say this is actually C. Yeah, so no, the period of data is 12 months. Okay, so we're off a little bit, but you know that's pretty good as far as what it would be. So we're 0.6 months short of the actual what it would be. Now D, we said the daily temperature it was going to be 92.5 something, 95. So we found 92.95 degrees Fahrenheit, or if we plug it in position this, 5 is going to round up to 9, that's going to go, so it's going to be about 93.0 degrees Fahrenheit going to that one decimal place. Okay. Now, does that fit? Well, July, we got 92.8. This shows 93, so yes, it's a close fit. Okay. And so that's how we're going to work with these, with the data tables. Again, we're just using our sine function, getting our function out, finding whatever else they ask for. The period, does it match what we're looking for? Not really, but it's close. And does it fit the prediction with what the actual table is? Yeah, that one was pretty close. All right, so let's stop there and we'll come back.